Okay, congratulations. I hear a noise, but okay. Um, Congratulations, everyone, for the presenters. All works as excellent. Okay, my name is Gaston. I am PhD student in the Universidad de la República in Uruguay. I will start with the presentation or work. The title is on the uses of generative model for network anomaly detection in multivariate time series. This is a work between the University of the Republic from Uruguay and the Austrian Institute of Technology. Okay. The first thing is to see what is the anomaly detection in multivariate time series. And then in the network monitoring, or more generally in the system monitoring, we can find different time series that represent the evolution of some variables or that are associated with the measurement or event counter. For the anomaly detection, generally are used semi-supervised methods, which have two phases. A training phase, where the method learns a model of the normal behavior of the series, and an application phase, where using this model to the method can identify anomalous pattern when they move away from the model. Okay, and then this kind of system generally have many different series that must be monitored. To simplify the first phase of the detection, we set out the normal behavior of all variables with only on a single model. And for that, we treat all the variables of the system as the variable of a single multivariate time series. Then, to create the model, we need tools that are capable for modeling data in a complex domain, okay? Because we are working with the sense 100 or maybe 1,000 of variables. And for this task, we choose two of the most popular tool of generative model, which are generally used with complex data, such images. We use the generative adversarial networks and variational autoencoders. A little bit introduction. The generative adversarial networks are two neural networks that are trained from a competition between them. On the one hand, the generator, we try to generate samples that are more and more realistic over the time. And in the other hand, the discriminator must increase its ability to differentiate when a sample comes from the real data of the generator. And when the training ends, the generator will be a very good model of the distribution of the real data. And then the variational autoencoder is a neural network with two parts, the encoder and decoder. And this is trained with the objective that reconstruction look more and more like the training data. When the training ends, the network will be a very good model of the distribution. Then, in our approach, the next is I'm going to show you how we use the generative model approach for detection in multivariate time series. First, we need to change the data space. We're using a moving window of length t. And we will convert the series into many small sequences that will our samples. And therefore, we work in a matrix space with the matrix of n rows is the number of variables of the system, and t columns that the length of the sequence. This is like a hyperparameter. Then, our main approach is the NetGAN, which continue with the architecture of the generative adversarial network. You can see the generator in yellow color here, and the discriminator in blue color. But we substitute the traditional convolutional neural network and fully connected network via recurrent neural network in the generator and in the discriminator too. With this, we can to explode the temporal dependence, okay, between the sequences. And then the training is some as a common generative adversarial networks. The only difference is that the generator and discriminator at the inputs and outputs work with sequences. And therefore, the generator inputs are random Gaussian noise sequences where each instant is independent of each other, and the outputs are sequences in the data space. In the case of this discriminator, the inputs come from the data space, and the output is a sequence of predictions. Okay, and each prediction indicates the probability that the value at that time in the sequences come from the dataset. Maybe this seems to make no sense in the training, but for the application phases, this is very important. Okay. Then in the application phase, once the training phase is finished, with this each time a sample arrives with the generator, we can generate the normal samples that more closely resemble it. Here, this is the real, this is the generator. And then we can calculate our residual loss between the two samples that real and generate. And from the size of the residual, we can determine in the, if there is an anomaly in which variable, this is important, it occurred and where inside to the sequence. Okay, what's the time is time. In the other hand, given that the training of the model was only with normal data is without anomaly, the discriminator is expected to return a low probability for the instant where an anomaly occurs because it does know this behavior, okay? So something like here and here. And then this only makes it possible to determine at which point in the sequences the anomaly occurs, but know which variable is affected. We call this discrimination loss. This is the NetGAN approach. The next approach is the NetBAL. This is method work in a simpler way. Here we not use recurrent neural network. After the data space change, we use the most common structure with fully connected network for the encoder and decoder too. Similar to NetGAN, the model is only trained with normal data sequences. So when training progress, the network is expected to learn the distribution of this data, similar to the generative and the other approach in the NetGAN. And then once the training phase is finished, because the model was trained with only normal data, it produces reconstruction that come from the normal data distribution. Okay. Then therefore, is the application phase. If a sequence show an anomaly, its reconstruction will be the normal sequence of the most closest resemble it. In this way, the detection is made by means of the residual loss too. After we developed our approaches and measured its work as expected, we tested them with two public data sets. The SWAT set contains 51 variables, which come from the sets of sensors that's monitoring a water testament system. This set has two parts this set has two parts, one without attacks to train the models, and other with attacks that have been labeled by time only. And the best results were obtained for the detection of residual loss, okay, both through approach, NetGAN and NetBAL. we can detect close to 70% of the attacks without false alarms. These results are very close to the state of the art. For the CI/CD 2017 set, this set has 80 variables. It's more bigger, and this belongs to the monitor of computer networks. We can report the detection performance of NetGAN and of the discriminator NetGAN. We only use the discriminator here. And in the SynthNet dataset for the 4 considered network attacks, about 93%, 100%, 89%, and 78% of the attacks are detected with a FPR below 1%. This for the attacks for botnet, infiltration, port scan, and DDoS, respectively. These results showing us a promising result to this specific scenario. Okay, this is the presentation of our work. The authors, we are all from Uruguay. Alicia Fernandez, Gabriel Gomez, and I, we work in the University of the Republic, and Pedro Casas is from the AIT from Vienna. Thank you so much for listening, for the opportunity to present my work here. Questions?
Thanks, Gaston. Let's see if there are questions.
I have a very quick question. Typically, neural networks are also have the advantage that they are fast, at least at the classification time. So, did you evaluate in any way how is the performance per se in the computation using the only at classification time? I mean, I don't care about training.
Yes, no, we have to work in this. We have another approach with a state of model. With a future work with this approach, we want to this work in real time. But we don't have a study of the time, but it's a work what we want to work this in the future. We don't have now numbers.
Okay, thank you. I think this is an interesting direction.
Yes.
Since it,
yes, we need to do this experiment because we want to use this in the industry.
Okay, thank you, Gaston.
Thank you.
Thanks. Other questions? Okay, since there are no one, I'll just give you a quick question. So, when you were presenting the window size, the length of the sequence, the one called T. I mean, what is the impact of changing the size of T for the performance, both in terms of accuracy and on computation?
Yes, this is because the parameter T is a hyperparameter. This is depend of the kind of data, because here we prove this with the stationary data. It's very important. Maybe if you have a periodic, it's very important to see what is the periodic in the data. But here we are looking the data and say, okay, we need to capture all day, for example, or all hour, and you prove this parameter T. But it's true that maybe we can use this like a hyperparameter and choose the best T in a validation set.
Okay, yeah, it would be interesting as a future work also to see exactly the impact and on both these aspects. Okay.
Okay.
So thanks, and we can move to the last presentation. So
yes.